Hey everyone, Mr. Newman here. Today we're going to learn about rational functions, talking about some asymptotes, and we're going to talk about how to graph it without a calculator, kind of like how we did with the polynomial unit, and we're going to use some similar strategies, so let's get started. First of all, I want to understand why asymptotes happen. So I picked vertical to start with, and I chose 1 over x to look at, our vertical asymptote. Notice I sketched in the dotted line there. Anytime you see a dashed or dotted line, either vertically or horizontally, that's representing an asymptote. And just as a refresher, if you remember, asymptotes are lines where the function gets closer and closer to that line. Sometimes you'll hear people say it gets closer and closer, never touches. That is true, except that sometimes, especially horizontal asymptotes, the function can cross over horizontal asymptote, but the idea is as you go out really, really far, it no longer crosses and simply gets really, really close to that value. So right here, this vertical asymptote is the line x equals 0, because it's vertical. And what I want to do is I want to build some intuition with this by making a table. So on this table, I'm going to look at values that get closer and closer to 0 coming from the right side, okay? So I'm going to look at the value of 1. When I plug in 1 to 1 over x, 1 over 1 is 1. If you plug in 0.1, see how I'm moving closer this way to the 0 from the right side, you get 10. Plug in 0.01, that's 100 because 1 over 100th is 100. And 0.001, the reciprocal of that, or 1 over that, is 1,000. So you notice what's happening as we're going left, as long as we're on the right side here. So if we're going left and getting closer and closer to 0 from the right, we go towards positive infinity because those numbers on the right are just going to keep getting larger and larger and larger. The way we say this with notation is as x approaches 0 from the right, notice that positive doesn't mean 0 is positive. It just means approaching 0 from the positive side, or from the right side. Then f of x is getting closer to infinity, positive infinity. Let's do the same with the negative side here. I'm going to make a table. If I look at -1, you plug in -1, you get -1. Plug in -0.1, you get -10. If the input is -0.01, you get -100. And if you put f of -0.001, then you get -1,000. Here what's happening is we're approaching from the left side this time, from the negative side, and we keep going down, 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 faster and faster as you get closer and closer to 0. So we're never actually going to get to 0, but we say this like this. As x gets closer to 0 from the right, that's this notation right here, the minus, not to the negative power, but from the right, or sorry, I said from the right, from the left, from the negative side. As x approaches 0 from the left, from the negative side, then f of x gets closer and closer to negative infinity, or goes towards negative infinity. Now, notice one other thing, you guys. If you plug in 0 here, you get 1 over 0, and you can't divide by 0, so that does not exist. That's not a real number. In fact, it's not even an imaginary number in this setup. So, yeah, we could go ahead and type that out, write that out. But anytime you have a vertical asymptote, you're going to have something that does not exist. Now, what happened here? Anytime you have a 0 in the denominator, that's when you're going to have, or you might have, a vertical asymptote. So I'm going to go ahead and make this rule. If you have a 0 in the denominator, then you're either going to have an asymptote, okay, or you're going to have a 0, okay, a hole. And let me just write that off to the side here. I realize that's or a hole. And we're going to talk about what holes look like on the other side. But yeah, if you have a 0 in the denominator, look out for an asymptote or a hole. For now, we're going to talk about as if they're all asymptotes. So on the right side here, you have 1 over, I went in and factored this for you, x minus 2 times x plus 3. Notice that x plus 3, if I plug in -3 into the function, you get 0 in the denominator. So we're going to have an asymptote at x equals -3. So vertical asymptote at x equals -3. All right. X minus 2, that's going to give us the one on the right because if you plug in 2 there, you get a vertical asymptote at x equals 2. So I'm going to put vertical asymptote at x equals 2. All right, I want to build some intuition with just one of these. Let me go ahead and work this out here for you. So if we plug in numbers that get closer and closer to -3 from the left side, that's going to look like this: -3.1, -3.01, -3.001. And if you plug those in into the calculator, you get larger and larger numbers. So that's how I know that on the left side of -3, x is going to positive infinity. So as x approaches -3 from the left, that's this notation right here, okay, x -3 from the left, then g of x is heading towards positive infinity. For the other one, we want to plug in numbers that are getting closer and closer to -3 from the right. So -2.9, -2.99, -2.999, and you notice what's happening is these are getting larger and larger in the negative direction. So we are going down, and that means as x approaches -3 from the right, this right here is g of x is going towards negative infinity. All right, so that's vertical asymptotes, and you can always figure that out by finding the once it's simplified. Find the zeros in the denominator. Any zeros, if it's simplified, they will be vertical asymptotes. All right, horizontal asymptotes, though, are a little bit of a different story. Let's build some intuition this way. So much is similar, yet there's enough different stuff that we should go ahead and graph these. So I'm looking at heading out that way. And you're going to see a chart that looks very, very similar. In fact, all we're going to do is switch x and y. In this sense, though, it's x that's going to infinity, and f of x, or y, is going towards 0. And the way we see this in a table is that x we're going to go to infinity by plugging in 1, 10, 100, and larger numbers. And you notice what's happening to f of x? It's getting smaller and smaller because 1 over 100 is 0.01, 1 over 1,000 is 0.001. So we're getting closer and closer to 0. We'll never reach 0, but that's getting smaller and smaller. On the left side here, instead of x going towards positive infinity, x is going towards negative infinity. So I'm going to plug in -1, -10, -100, and see more and more negative numbers. And you notice what's happening. The -0.1, -0.01, -0.001, those are getting closer to 0 from the bottom. What's interesting is we don't really care whether it's getting closer to 0 from the top or the bottom in this setup. So all we need to do is just write down x as x is approaching negative infinity. F of x is approaching 0, getting closer and closer to 0. All right. On the right here, I've got another horizontal asymptote that's a little bit different. It isn't always at 0. Usually it is if there is one, but often, sometimes it's not. Here we have a horizontal asymptote at y equals 2. And you notice right here what happened. The graph crossed the asymptote. So you have to be careful when you say it never touches the asymptote. Well, what I'm talking about is as we go out this way, that part of it, and as we go out to the right, that part of it, those are never going to touch the asymptote. But you can touch the asymptote. You can cross over it when you're in, we'll call these normal numbers in a reasonable domain. All right, so what's going on here? Well, let's plug in some numbers into g of x. If I plug in 10, that's a big number, you get 1.77. If I plug in 100, you get 1.97. Plug in 1,000, you get 1.997. So you can see from the table, it's getting closer and closer to 2. Well, the way we write this, as x approaches infinity, g of x is approaching or getting closer to 2. And once again, we don't care about whether we're getting closer from the bottom or the top, but you guys can see on the right, this side is clearly getting closer from the bottom of that asymptote. For the negative side, when we plug in -10, we get 2.3. Plug in -100, you get 2.03. Plug in -1,000, you get 2.003. So as we are approaching negative infinity, and in other words, if we're going left as fast as possible, g of x, our y value, is getting closer and closer to 2, and this time it's getting closer from the top, right up there. So what's the deal here? What's going on? Well, I want to zoom in on the function and look specifically just at the first terms. We call these the leading coefficients. The leading coefficient of the top is 6x squared, and the leading coefficient of the bottom is 3x squared. If you remember from our polynomial unit, when you look at a polynomial, really big positive or really big negative numbers, when you plug those in, the only number that matters is the leading coefficient because everything else is small by comparison. So what we have here is we have a really, really big number plus some other junk divided by a really big number plus some other junk. And what I care about, I don't care about the junk there, I care about what's the ratio of the top to the bottom. In this case, because the x squareds are even, no matter what big number you plug in up here, you're also going to plug in the same one there and get the exact same number out. So we can simplify this, say 6x squared divided by 3x squared, and we get 2. That's why 6 divided by 3 is 2, so that's why these numbers, the bigger numbers you plug in, the more positive or the more negative, the further away from 0, the closer this thing is going to approximate just plain old 2. Okay? On the back of the sheet, we're also going to talk about more details about the horizontal asymptote. This is where the idea comes from. All right. Let's now flip over to the back, and we're going to use this function right here, f of x. For most of this, the only exception is the simplify one. Since this is already simplified, I'm going to give you guys a different function for simplified. So write this down real quick. G of x is x over x times x plus x times x minus 1. I can simplify this. You know there's an x on top. Notice there's an x on top and an x in the denominator. So I can divide those two out, and we get 1 over x minus 1. Well, except I need to put a big star here. Anytime you simplify by dividing something that has an x, you need to watch out, because if I plug in a 0 here, doesn't matter what I'm multiplying on the denominator, I'm getting 0 out in the denominator. So I'm not allowed to plug in 0 into this function. So the way I'm going to represent that is I'm going to put here, oh, cautious, the domain cannot include 0. I'm not allowed to plug in 0 into this function. So x cannot be 0. What that's going to do is when you graph this later, that's going to make a hole at x equals 0. Whatever y value that would be, it's going to make a hole. And we're going to do some more practice with this, but just to give you a quick idea, if you remember, it's like a normal function, you just sketch it, but then wherever that, for example, this would be 0, wherever that hole is, you just make an open circle, which means you can't have the number there, okay? All right, so that's simplifying. Just be careful when you're simplifying that you are writing down the holes you get and making notes about what the domain can and can't be. Back now, we're going to come back to here. I'm going to use this f of x for all the rest of these. So let's use it for the y-intercepts. The way you find the y-intercept is you plug in 0. So I'm going to plug in 0. F of 0 equals 2 times 0 minus 1 over 0. Well, that's a problem because you can't divide by 0. So there are no y-intercepts, and we're going to see actually that is a vertical asymptote at 0. And often that's what happens when you get something that does not compute when you plug it in. All right, for x-intercepts, the way you want to do this is any x-intercepts are where the function's equal to 0. Well, if the denominator is 0, we get a vertical asymptote. If the numerator is 0, that's when you get a 0. So we want to set the numerator equal to 0. Set it equal to 0. Anytime the numerator is 0, that's where our zeros, our x-intercepts, are going to be on a function. Solve this, you get x equals 1/2, so one of these zeros, in fact the only 0 we have, is x equals 1/2. Alright, for vertical asymptotes, we already talked about that on the front of this sheet, but that's when the denominator is equal to 0. So once again, you want to set that equal to 0. So from my function, it's a little weird up here because x is the only thing in the denominator, so I'm going to set it equal to 0, and there, I'm done solving. X equals 0 is a vertical asymptote. We could have known that because we also talked about that up here. But yeah, anytime you plug in 0 and you get 0 in the denominator, that's going to cause problems. Now, with horizontal asymptotes, I'm actually going to give you a few notes here, some guidelines for how to figure out what in the world happened on the front of this sheet. You always want to look at the leading coefficients like we talked about. Let's say these are the leading coefficients. I just threw some numbers out in front. Remember, the 3 and the 2 don't matter out in front. It's the squared and to the 5th power. We care about which leading coefficient has the larger degree. In other words, which power is the bigger power, bigger exponent. X to the 5th, if we have the denominator has the bigger exponent, then what happens is the horizontal asymptote is going to be at 0, at y equals 0. The reason for this is when you plug in really, really, really big numbers, whether they're positive or negative, that denominator to the 5th power is always going to be way, way, way bigger than the number on top. Okay, so the thing that gets overpowered, any number divided by a really big number, is going to be getting closer and closer to 0. Okay, really, really small, so we'll get really close to 0. Let's say that the exponents or the powers are the same degree on the top and the bottom. Well, then the horizontal asymptote is going to just be the top coefficient divided by the bottom coefficient. In other words, here it's 5/3. So 5/3 equals y would be the horizontal asymptote. That's what happened on the front. We had 6 divided by 3. 6 over 3 is 2. So 2 was the horizontal asymptote. Y equals 2. Well, what if the opposite happens? What if the numerator has the larger degree? In that case, we just get a really big number, so that is no horizontal asymptote, and it will act more like the polynomials we've learned about before, where it's either gets really, really big positive or really, really big negative. There is one special case, and that's we're going to talk about on the next video, are slant asymptotes, but let's not worry about that quite yet. All right, last thing we can have to do before we plot the point is we need to, sorry, let's talk about the horizontal asymptotes here. I'm looking at 2x minus 1 over x, that's f of x. So 2 over 1 means our horizontal asymptote for our function here is at y equals 2. All right, where do we plot more points? We want to plot more points, find more points between every vertical asymptote and every 0, and on either side of those. So what do I mean by that? Well, here I'm going to make my table horizontal because I ran out of space. So got the x values. For one thing, we found there's a 0 at 1/2, so I'm going to write down 1/2 and then 0. That is 1 point. And then the other point we know is that when we plug in 0 to this, then the x is 0, we know we have an asymptote there, okay? So we want to find between 0 and 1/2, pick a simplest possible number and calculate what that output is. So 1/4 is one of the numbers we want to look at because that's between 0 and 1/2. But we also want to look on the left side of 0, that's -1. I just picked -1 because I thought that would be an easy number to plug in, and we'll see it works out very nicely. And then on the right side of 1/2, we want to pick another nice number. I'm just going to pick 1 because that's about as easy as you can pick to plug in. So I'm going to find out the y values of these just by plugging them in. When I plug in -1, I get 3. Plug in 1/4, I get -2. And plug in 1, I get 1. And let's do this. I'm going to write all those down right here. Those are going to be what's going to help us. So first, make your axes. Label a few values. You notice I picked some that made sense to me because I noticed the y goes all the way up to 3 and the x goes all the way down to -2 as far as the points I found. So I definitely want to include those. And I also then want to plot my asymptotes because that's going to kind of make a boundary for my function. So vertical asymptote, I hope you can see it there. I'll write it up here. The vertical asymptote is at x equals 0. And the horizontal asymptote is at y equals 2. Okay? So horizontal asymptote at y equals 2. Always do your asymptotes first because then the points you make and the lines you connect won't accidentally go through them in the wrong way. Now, notice on the top left there, I know -1, 3 is a point. I also know that 1/4, 2, 1/2, 0, and 1, 1 are all points. So I'm going to make those, and you can start to see a shape here. I happen to know what this looks like because I know what 1 over x looks like, but the hyperbole. But what you want to do is you want to plot more points if you're still unsure about what this looks like. So I'm going to go ahead and connect the dots and draw the lines I know exist. Notice how I got closer and closer to those asymptotes without touching them. And that is how you graph a rational function. We'll be doing lots of practices in class with multiple vertical asymptotes and multiple zeros and even holes. So come with questions and come ready to learn. Thank you for watching. Have a good day.